All right, the next speaker of the session is Carolyn Wood. She's going to at the University of Queensland, and she's going to talk about quantized mass energy effects in a particle detector. Carolyn, the floor is yours.
Thanks, Eduardo, and thanks to all the organisers for making this week happen. It's great to see some familiar faces and names up there, but of course I'm looking forward to seeing you all in person again soon. Okay, so today I'm going to talk to you about some work contained in our recent paper here, in which we incorporate mass energy equivalence into an Unruh-DeWitt detector model. So I'll start by discussing why we might want to add mass energy equivalence into a detector model, and then I'll briefly look at a couple of previous models, in particular the basic definition of the Unruh-DeWitt detector, which we're building upon, before getting into the new work we've done and what we've learned. So there's a reason the Unruh-DeWitt detector features in so many of the talks this week, and that's that it's a really useful toy model. It's simple and it can be adapted for a variety of situations where a quantum particle interacts with some environment. For example, atom-light interactions. Now, in atomic physics, mass energy equivalence has been shown to play a role in these interactions. So this work by Sonnleitner and Barnett is a well-known example, but they certainly weren't the first to notice this effect. What they found, though, was that an atom moving through the vacuum experienced a friction force in proportion to its initial momentum. And this effect would appear to violate conservation of energy and momentum, but it disappears when one makes corrections which allow the mass of the detector to change. So these mass energy effects are important, but as members of this community have identified, the Unruh-DeWitt models which we've seen so far cannot fully capture these effects, which is where we came in. Oh, okay. But first I'll give a quick overview of the detector we know and love. The common model consists of a point-like particle linearly coupled to a quantum field traveling on a classical trajectory. The interaction with the field is always restricted to a particular location in space-time, and only its internal state is a quantum degree of freedom. Hence, in the free Hamiltonian, we only have two terms, one for the internal energy and one for the energy of the field. In the cases I'm considering in this talk, we're going to use a two-level system. So the detector's internal state has just a ground and excited state, and it can emit or absorb packets of energy to and from the field. Now, there's been recent interest in some more quantum features in the detectors. For instance, there's this work by these two groups here, where the detector follows a superposition of classical paths. And then there's also this model, which adds a quantized center of mass. So the free Hamiltonian picks up a term for the center of mass's energy, and the center of mass can be described by some wave function which can spread coherently. I'm going to refer to this model as the non-relativistic model for the rest of this talk, for simplicity. So in my model, I bring in the relativistic corrections to the center of mass via the mass energy equivalence, and that essentially turns the mass into an operator. In the low energy regime, where the previous model has also been conceived of, the detector now has this rest mass energy added to the aforementioned center of mass. And for our two-level system, M hat breaks down like this. So there's a mass associated with the ground state and the energy state, and the excited state. And ME and MG differ by the energy gap in the detector. So E now plays the role of the energy gap, but also this gap between the masses. So what does this mean for, say, emission and absorption processes? So looking first at the emission process, we have a system beginning in a state where the detector's center of mass is in some generic state here. It's in the excited state. The internal state is excited, and the field is in the vacuum state. and then it drops to the ground state, emits a packet of energy into the field. And in the transition amplitude, which we've calculated here to first order in perturbation theory, we can see the conservation of momentum here in the wave function. And under the time integral here, we see that the masses do indeed play a role. And we can see how the changes in mass and energy are expressed here. And if we take these bounds to infinity, energy is conserved. Then for the absorption process, we have the opposite situation where energy from the field excites the detector, and you can see the signs on the exchanged momenta and energies are reversed. So that is looking pretty neat. So most importantly, the mass energies do indeed have some sort of effect in the transitions, but the question then is, how big is that effect? So here I compare the emission rate to that of the previous non-relativistic model. And on the x-axis here, we have the initial spread in the center of mass momentum. And the solid lines here are our model, and the dashed lines are the non-relativistic model. So firstly, we see a clear difference between them, and that the additional mass energy in our model is suppressing the emission rate compared to the other model. So this effect increases with higher initial momentum spread, and that's because there are more higher momenta contributing to the initial state there. And the difference between the ground and excited mass energies then consequently becomes more significant. The difference is more marked in the bottom plot here, as the energy gap is included in our definition of the excited state mass. So why do I have two plots here? Well, the question arose in the course of this analysis, which mass in our model should be compared with the fixed mass of the non-relativistic model? We might initially think that it should be the ground state mass, but then is that also true for the absorption? So we decided to remain agnostic and look at both options. So on these plots, our model is held fixed. So the solid lines are held fixed between the two, and the non-relativistic curves are changing. And then we make the same comparison for the absorption rate. And we also looked at the rate dependence on the energy gap, but I've excluded those plots here in the interest of time. But you can check them out in the paper, or you can ask me about them later. As for the question of which mass is the correct mass for the comparison, well, the resolution lies in looking at the non-relativistic limit for small values of the initial center of mass momentum spread. So in short, the solution is not that one particular mass is correct for all processes, but it's in fact whichever mass is the final mass in the given process we're looking at. So for absorption here, the correct mass to compare is the excited state mass, and for the emission, it's the ground state mass. So that's an interesting little result. It was a somewhat surprising finding along the way. But the question we really want to answer is, what's the extent of the effect of the relativistic corrections that I've introduced? So you might be thinking these changes in mass due to the internal state transitions must be really tiny. But if we look at the rates of the two models to lowest order in E on mg c squared, the two models are quite similar. So we posit that if we want to include center of mass dynamics in the detector model, we must also include these mass energy corrections. Ripping through this. So to summarize, the relativistic corrections that we've added persist even into the lowest energy regime, where one might expect that that would not be the case. And those effects are on the same order as the center of mass dynamics themselves. So we're positing that mass energy can't be ignored if any dynamics are to be included at all. And then we had our extra unexpected result that the final mass after transition is the correct choice when comparing with the fixed mass of the non-relativistic model. Some questions we're left with, or ideas for future work. Well, in this model, there's entanglement between the internal degrees of freedom and the center of mass degrees of freedom. So it would be interesting to see what that means for an entanglement harvesting scenario. And as Magdalena mentioned in her talk last night, we're interested in the Tolman-Ehrenfrost effect, which involves both a gravitational field and a thermal field. So perhaps this model could help us probe that environment. Here's a link to our paper. And if this work piqued your interest in some way, please get in touch with me here. And I'll also keep an eye on Slack for the rest of the week. Thank you.
All right, thank you, Carolyn. Really good talk, really interesting talk. Okay, we have time for one question. Okay, I don't see any hands. So I can ask one question. So have you identified any regimes where neglecting this, but having some degree of dynamics could be, because for example, when we looked at, of course, superficially those things with Richard, there were some regimes, sometimes the effects are suppressed. Now, of course, the same order, I agree, but they're sometimes suppressed under some assumptions. And I wonder if you know of any regime where you can still consider some internal dynamics, but these effects are more negligible than others.
Forgive me, I'm a little bit tired and having trouble accessing information in the back of my mind at the moment. But
no worries.
I do feel like I have come across something to that effect. I'm not sure how robust the thought was, but if I recall it again, I'll let you know.
Right, no worries. All right, if there are any more questions, then let's thank Carolyn again.
Thank you.
And again, thank you so much for the extra sacrifice that you have to do in order to be here so late. We appreciate it.
Oh, it's okay. It's just nice to be involved with the other time zones.
It's a pleasure to have you.